A wonderful welcome to this Ask the Pro series. We'll just give a couple of more seconds for people to join. And while people have this chance to join, I wanted to talk briefly about the Coffee Technicians program. So if you're interested in developing your skills as a coffee technician, you should definitely check out the Coffee Technicians program, which is an education program for new and experienced technicians alike. And there's 3 levels available. They're foundation, intermediate, and professional. And the overall program consists of 6 modules. So it's coffee machines, hydraulics, electrical, water and preventive maintenance, operations management, and coffee preparation. So if you're interested in learning more, finding out what this program is about, how to get involved, how to take some classes, make sure to go to sca.coffee/coffeetech. That's sca.coffee/coffeetech. And without any further ado, I will hand over the digital microphone to Hyland.
Actually, Caleb's going to be doing the introduction.
Oh, Caleb. Oh, sorry. Like Caleb.
It's okay.
Caleb's got the radio voice.
Thanks. You want to go to the next? There you go. So this is the Ask the Pro series, season 3. We're committed to presenting these episodes throughout the year. So save Fridays at 8 for the Coffee Tech Guild. I do apologize. They're picking up the recycling, so I can't stop that noise and talk at the same time. There's no mute for that. This presentation is for informational purposes only. The views and opinions expressed in this webcast are those of the presenters and do not necessarily reflect the official policy or position of any aspect of the Specialty Coffee Association or the companies the panelists may represent. I'm going to get that in one breath eventually.
Yeah, it was good.
So this is the part in our show where we do some quick introductions and just, say what coffee we're drinking, or if we're not having coffee right now, maybe what our favorite coffee is. I'll go first. I'm Caleb Leach. I've been in specialty coffee industry since 95. Started out as a coffee roaster. I parlayed that into a equipment technician job. Owned a cafe for a couple of years, but for the most part, I have worked as a technician or managing technicians in my career. And currently, I'm at Starbucks as the equipment services manager. And this morning, I'm having a delicious Burundi I made with a pour over, and it's a natural processed. I got a lot of floral notes, a little bit of citrus. I'm gonna say some blueberries, because it's sweet, and that's where I tend to go. So let's see. Let's go to Michael, since you're going to be our speaker today.
Can everyone hear me okay?
Yes.
I trust. Let's see. I've been doing coffee since '87, I think, 1987. Started working with an importer, Michael Espresso, up in Seattle, selling espresso machines in Portland. At the time, there were very, very few Starbucks. It was kind of like the new kid on the block. And I, like you, I have owned cafes, designed espresso carts, I just gravitated toward the technical side of things and trying to figure out how things work. So the reason I do this is because that's where my passion lies. I tinker a lot. Gosh, for coffee, Ethiopian Yirgacheffe has a latte every morning on the dark side. It just tastes like coffee. I don't know. I'm old school. I'm old fashioned.
I don't think there's any wrong or right there, Michael.
Okay. Am I kicking this off, or Hyland, you want to step in for a second?
Oh no, actually, I'm going to go next. And Kurt, will you do a quick introduction?
I didn't mean to cut you off. Sorry.
Oh no, it's okay.
Good morning, everyone. My name is Kurt Benedict. I run Last Man out in Colorado. We are a small service group. Right now, I had a nice Ethiopian not Ethiopian, sorry, I heard Michael. No, I had a nice Guatemalan from a local roaster called Pablo's. Really good, nice, clean. Love the caramel notes on it. Love them. So that's about it for me.
Thanks, Kurt. Matt?
Hey, yeah, I work with Fixo. I'm the lead technical trainer there and support. I've been in coffee not as long as Michael or Caleb have been, but for a little bit here, kind of dabbling in anything from behind the bar, doing you know, bar flow setups with other companies, and you name it. So I've kind of had my hand in just a little bit of everything. So yeah, today I'm drinking a Guatemala from a local roaster over in Louisville called Quills. So it's quite nice. It's got some cranberry and kind of like peach syrupy notes. So yeah, really nice.
Thanks, Matt. Highland?
My name's Highland Joseph. I am West Coast service manager for Espresso Partners, and I got my first barista job in '85. Actually cracked my jaw on an old piston machine, so I have my first scar from it. Currently, I'm drinking a coffee from the Congo, and apparently I'm the only one that didn't know Congo is a producing country. So has anybody had coffee from the Congo? Any beans?
Mhm.
Yeah, they're like fantastic, but this coffee, like unusually, I actually made it fresh this morning, Caleb, just so you know. I wasn't drinking shitty old coffee, but it's actually fantastic. So if you get a chance to try some Congo beans, I recommend them.
Nice. Thanks. And I think Michael, I think we've worked together over the years as a technician. I remember reaching out to you for technical support on I think it was a Rosito Bazzani super automatic.
It needed a lot of technical support.
Yeah, and you were there for me. I really appreciate that. While I cursed the machine, at least I had someone to help me walk through it. All right, Highland, I'm going to kick it over to you.
Okay, Mike's going to go through pressure and flow, the relationship between them and how to manipulate them. This comes off of a conversation at one of our digital content meetings where Jake Chivario asked about gicleurs, and it went into about an hour conversation where Mike kind of explained the flow, and we decided it would make a really solid episode. So Mike, I'm going to turn it over to you and just say slide when you're ready to go.
Okay.
Go, my man.
Pressure and flow is kind of like a relationship. Understanding, you know, how everything works in an espresso machine. There are certain things that you can manipulate and certain things you can't. A lot of it has to do with the way the machine is designed. But just getting to fundamentals, you can have pressure and you can have flow. You can have both, but they're actually linked, but there's a relationship between the two. So the picture on the top shows what it looks like when you have flow but no pressure. So if the pump is just running, for instance, if you just hook up an espresso machine pump and just let it free flow, there's actually no pressure coming out of the pump. You have straight flow because in order to develop pressure, there has to be some kind of restriction. You have to have some kind of closed vessel that you're trying to pump into, or a restricted closure of some kind. So the second picture shows what it's like to have pressure but no flow. But I've tried to kind of color code it. So when there's a dark color, that means that the pressure is higher. So when you have a closed system, so for example, you've got a 3-group espresso machine, and you know if the pump is running, for example, and no coffee is flowing, no water is flowing from the group, that's a closed system. And so the pump can be running and developing pressure, and if there's no flow, no water is actually moving. So the pump is sitting there spinning, and the adjustment for the pressure, which is actually at the pump head, which is a spring regulated pressure adjustment, is bypassing all the water back into the pump. So that's kind of what's happening. So the restriction itself is kind of the fundamental requirement to actually develop pressure. So let's go to the next slide. And hopefully this presentation doesn't only take 5 minutes. So like in a normal espresso machine, the top picture shows what it's like when you're maintaining pressure with a nominal flow. So you're delivering 25 cc's over the course of 10 or 15 seconds. The motor and the pump are able to generate, in the case of an espresso machine, 9 bar pressure in a restricted environment. So because water is always bleeding from the system while it's running. So the power of the pump is necessary to generate the pressure in a variety of environments where the flow rates may change. Like for instance, in the second slide, if you've got 2 groups running or 3 groups running all at the same time, the pump has to be powerful enough to generate enough pressure so that it can maintain that 9 bar of feed pressure to the system, even though you have more actually water flowing through the system. And in the case of the third picture, if you might find like smaller pumps even on 3 and 4 group machines, especially when manufacturers are trying to kind of cut back on the number of pumps that they provide. Sometimes you might see on a 4-group espresso machine, if all 4 groups are going, your pressure is actually dropping. And that's because, the pump isn't able to maintain enough pressure with that amount of flow. So, that relationship between, the pressure in the system and the flow in the system is really about system design, how they've engineered it, how much power they apply to the pump and things like that. So hopefully that's kind of clear. Here, let's go to the next slide. We're going to talk about different ways that pressure is maintained.
Really quick question.
Yeah.
Some manufacturers do their brew boilers. Their brew boilers is like you'll see two groups, 2 boilers for two groups. Mm-hmm. Sometimes even single boilers. Does that make any difference in the jet effect?
No, actually it doesn't. Everything comes down to system restriction. If you think of flow kind of like a highway, for example, so you've got a 3-lane highway, everyone's doing 30, 40 miles an hour. You've got so many cars that are able to flow through that highway. Now, if you take it down to a 1-lane highway, in order to get the same amount of flow, you have to increase the speed 3 times. So essentially, the flow rate is kind of a function of like speed and power, or kind of like a way to describe, how to accomplish both of those things. Because on the water side circuit, on the brewing circuit, whether it's a single boiler with a heat exchanger, a dual boiler with a dedicated water boiler, or even individual boilers, unless you're actually breaking down the individual boilers with individual pumps, like some machines are doing now, the restriction calculations are the same. If you have one group open, it's going to be more restricted than if you have 2 or 3 groups open, and that is a function of the pump's ability to maintain pressure. So in terms of the pressure, flow, and restriction really is kind of the key to understanding how flow happens. So in terms of the relationship between all 3, pressure is essentially a force, the ability of the machine to maintain that pressure. So you'll have different size motors and different size machines. When you have larger machines, oftentimes you'll have larger motors, and those larger motors are in order to enable the pump to maintain speed and maintain pressure even when the flow rate is significant. That's why you'll find larger pump capacities and larger motors on larger machines. In terms of regulating the pressure, on traditional conventional espresso machines with conventional pump arrangements, there's a pressure regulator actually attached to the pump. And so in a sense, the way that the pump is regulating pressure is with a spring-loaded bypass. And the idea is that anything that exceeds 9 bar or whatever you choose to set it for is simply bled back into the system. So anything coming out of the pump is actually spring regulated to 9 bar, so it'll never exceed 9 bar. In some, but it may be less if it can't keep up. For example, if the flow rate's too great. Now we get in terms of the flow side, and this is where the gicleurs come in, or I simply call them jets because it's easier to say than a weird French word, but the jets are about metering. So really what jets do and what gicleurs do is they regulate flow. They have an impact on pressure because of what the pump can actually generate, but really it's about regulating the flow rate so that the flow rate is either gradual or it builds at a specific rate, or it allows the distribution of water over the coffee in a certain way. Typically, so the things that can affect the flow rate are things like flowmeters, jets, even a solenoid valve on a group head. because not all machines have flow meters, not all machines necessarily even have solenoid valves. But to understand, how jets work, it's, water you can only move so much water through an orifice at a given pressure. So when talking about a flow meter, for example, a flow meter really doesn't measure volume. A flow meter doesn't measure cc's. What a flow meter does is it measures flow. So in the flow meter, there's a 1.2 millimeter jet on the inlet side, and when you apply pressure to that jet, and there's an open circuit on the other side, so water can actually flow. What it's doing is that jet is creating literally a jet of water, and it's pointed at the impeller in the flow meter. So it's actually measuring the speed of that impeller. And then the computer in the machine calculates how much volume is moving based upon the speed of that impeller, because the speed of the jet the speed of the water coming out of the jet is a function of pressure and flow. So it can actually calculate very precisely how much water is flowing through the system by measuring how fast that flow meter reel is spinning. So in a sense, it's actually measuring the force of the jet. So if there's any obstruction, or if the size of that orifice changes from calcium or something like that, it's going to change the force of that jet, and that's going to affect how the whole system measures water, for example. In the case of jets, like typically we go into a group head, you can have different sizes of orifices depending upon the pumps that you're using, the distance between the jet and the outlet of the water from the group, because it regulates how quickly and how completely the puck saturates with water. But generally, jets are pretty much required, just to make everything kind of work. The other thing that jets do, and all these restrictions do, is it allows you to build pressure in the system so that you can actually set a benchmark for the pressure. So when we set 9 bar at the pump, really what we're doing is that's like the foundational starting point. Everything else that happens after that is based upon that fixed number of 9 bar. If you adjust that 9 bar down or up, it's going to affect the pressure throughout the whole system, because every restriction after the pump is a fixed restriction. So you can't actually adjust those. So that's that's all part of the system design. The one thing that you can adjust, the one thing that affects all of this, we're going to bring up at the very end. Because of all the things that you can do besides adjusting the pressure regulation at the pump itself, there's only one thing that you can do to really fundamentally address the flow and the pressure inside the machine. And that's going to come up at the end. Next slide, Highland. So, the ways that we can actually regulate and flow and pressure of the machine has evolved, over the last few years. And initially it was simply a lever machine with a big piston with a big spring in it. And then in the early 60s, everybody started moving over to pumps. And pumps were kind of a fixed pressure. So as soon as they come on, bam, you've got 9 bar. It's got a capacitor start. It whips up the speed very, very quickly. And because it does that, you had to regulate and kind of slow it down as the water approached the coffee. And that's why we have, pressure bypasses, and that's what we have. That's why jets actually started coming into groups. But now we're finding different ways to regulate flow and pressure. So with variable speed pumps, for example, you can have if you have a variable speed pump on each group head, you can actually replicate what a jet might do, for example, by ramping up the pressure very, very slowly, because you're actually regulating flow from the pump head itself. At that point, the restriction itself is what's going to be regulating the pressure. So you're basically replacing a pressure regulator and the dynamics of the jets and the gicleurs with a variable speed pump. But you have to have electronics and programming to do that so that you can kind of fine tune what's happening. So in the case of a variable speed pump, in the second picture, you can regulate both pressure and flow. So during a pre-infusion cycle, for example, the pump's only running at 500 RPM, and depending on the restriction that's actually in the coffee bed or in the brewing group, you can increase the pressure by simply increasing the speed. You can also increase the flow, so it's kind of dynamic. Whether if you're simply free flowing the group to kind of flush it, it's going to be operating at a different speed. I threw the vibration pump in the bottom as a way to regulate flow and pressure because vibration pumps behave a little bit differently than a conventional rotary pump. They can develop very high pressures, but they build pressure very slowly because they don't move very much volume. Whereas a large rotary pump is designed to move a great amount of, a great amount of water, a great amount of pressure in the very beginning. A vibration pump builds pressure more slowly because when it has to fill the whole system, it's moving water at a reduced rate. So one of the manufacturers I worked with in Italy, when he was designing super automatic machines, actually preferred using vibration pumps because they were more adept at pre-infusing the filter bed with water because they were able to build it more gradually. So the reason I included it in there is that you can actually design a whole system, between pumps and jets and flow rates, or to deliver the best cup of coffee that you can, and you can manipulate that from a design standpoint from the machine. Okay, let's go to the next slide. Okay, so jets only really function when water is flowing. The effect of what they do is only important when water is actually moving through the system. So when a system is at rest, for example, what I've laid out here in the diagram is we started with the pump, and we're kind of measuring pressure all the way through the system. Sorry if my finger pointed in front of my camera. So when the machine's at rest, if you're feeding 3 bar to the machine, you're going to get 3 bar everywhere, before the flow meter, after the flow meter, after the jet, right up until the solenoid valve. And this is a completely saturated circuit. And what saturation means is that you've got a complete water column. You're not trying to fill a void that has air in it. You're not trying to fill a void that may have steam in it. There's no way for that water to expand. So it's a solid saturated circuit. And so when nothing is moving, everything is equalized. When you first push the button to make a cup of coffee, then things change, because at the solenoid valve, now you've opened up the solenoid valve and you've opened it up to essentially to kind of quasi-atmospheric pressure. Now things are flowing, and now you've got a pressure differential on one or the other side of a restriction. So there's the first pressure differential happens after the flow meter, and this is only while you're kind of that pre-infusion stage, when you have an imbalance in pressures in different phases of the machine. Generally, the gicler is typically like a 0.7 millimeter orifice, whereas the flow meter is a 1.2 millimeter orifice. So as soon as you open up the solenoid, you'll have this pressure drop on the output side of the gicler, because you're pre-infusing. You've opened up the water to space. It's kind of like that very first slide where you're dumping water into an open container. Now, as that pressure builds, because it's wetting the coffee and things like that, it begins to balance. But what's happening is, you've got a high pressure side on one side of the gicler and a low pressure side on the other as the water begins to flow. But every time that you have any kind of restriction, there's flow happening, there is a little bit of a pressure drop at each one. That's why, when in this example, the pump is feeding at 9 bar to the flow meter. It's passing through the flow meter as the water is moving. You get a little bit of a pressure drop on the other side of the flow meter with that small restriction. Then you hit the gicler, and the gicler has an even smaller restriction, so you have a bigger pressure drop on the other side. And so and then when it passes through the solenoid valve, by the time it gets the coffee, because that pre-infusion stage, that's when you get the biggest pressure drop on the coffee side. Now, if you change the size of the gicler, you can increase or decrease the amount of time it takes for that pressure to balance over the coffee bed. So you can actually increase or decrease, how evenly that water is able to distribute over the coffee. And let's go to the next slide. So when you're actually brewing coffee and the system is fully saturated, you see the pressures really begin to equalize. So you'll have 9 bar on one side of the flow meter, typically 9 bar on the other side of the flow meter. You'll hit 9 bar on the other side of the jiggler. You may lose, a half a bar as the water is flowing. But inside the actual brew chamber itself, you're not going to really hit 9 bar unless you have a really, really big pump that's driving a lot of water, because you're actually relieving the pressure from the system as the coffee is actually being brewed. So you'll get a little bit of a pressure drop actually in the chamber, in the group itself, just above the puck of the coffee. But without that initial 9 bar and then calculating the flow rate, through the system, through the jiggler, you're not going to get a good, a predictable pressure actually in the group itself. And so that kind of comes down to, what you can do in terms of actually regulating the pressure inside the machine. Because the brew pressure actually in the group itself is regulated by the filter bed, the consistency of the filter bed, the fineness of the grinds. So ultimately, it really comes down to the one thing that a barista or a tech can do to regulate actual system pressure or extraction pressure in the group has to do with the grind of the coffee. So if you have a very fine grind, for example, and the pump is working properly, you might hit the full 9 bar just above the coffee, because very, very little flow is happening. If the grind is much coarser, or if the consistency of the bed is irregular because the burrs are worn out and the flow rate is greater, you're not able to maintain, you're not able to actually reach 9 bar. So one of the reasons why coffee comes out like crap sometimes when it's coarse is because the machine isn't actually able to develop enough pressure above the filter bed to get the extraction that's needed. So when everything is fully saturated, you're no longer filling voids. You're not the puck is completely soaked and completely saturated. That's the maximum restriction you're going to have, and the only variable for the restriction is actually the coffee itself. So everything else is fixed. Everything else in the system is just is the way that it is. The only variable that we have is the coffee. So that's essentially what's happening inside the group. So that has to do with that. I think that we've kind of covered how flow works. But why it's important, why jets are important in espresso machines, actually comes in the next slide. The real reason that a jiggler exists is kind of wetting the coffee. So when you have a gradual, whenever you take a brewing group apart, you've got the screen, you've got the shower. In some cases, you have a dispersion plate even above, or the screen, the shower, which is the dispersion plate. In some cases, you even have a plate above the dispersion plate. The whole process is to allow the water to kind of fill up all the voids before it actually hits the coffee bed itself. And if you have too high of a flow rate, like so let's get back to the gradual pressure ramp. So the idea is it's going through the system that the water is distributed more and more and more. So basically there's typically one port that enters the group, then that port then goes into a small void above the shower holder. The shower holder will have 6 or 12 or whatever number of holes that are evenly distributed around where the shower is. And so what that does is that distributes the water evenly over the shower. And then the shower has a multitude of holes that's also designed to distribute then that water evenly over the filter bed. And then that void, what's called headspace between the top of the puck and the shower itself, that's ultimately where all the water develops. And you want that to be an even, low pressure, complete filling of that void really before water is allowed to penetrate the puck. Because if the water flow is too great, what happens is on the right-hand side. So if the water flow is too fast, it doesn't have a chance to actually fill those voids above the shower holder, above the screen, above the headspace evenly, because the water is flowing too great. So I've seen this on like E61 groups that'll have like a 1 millimeter jet, for example, maybe because they were using a a vibration pump in one machine and switched over to a different kind of pump. If the flow is too great, the water will typically bias to one side or the other, and this is what will generate channeling in the puck. So if one side of the puck actually gets water before the other, the water begins to penetrate that puck, and it does so unevenly. Because even though it's you're kind of exposed to some degree of atmospheric pressure, as the restriction develops, you're also kind of pressurizing the air in the system. So if it's going too fast, then you'll get an imbalance. So then you get uneven extraction, and that's how channeling occurs. So for example, if you've got an espresso machine and you've got a bottomless portafilter, and you're seeing that the coffee is biased, or the extraction is biasing to one side of the shower over the other, and you've fixed everything else. You've got fresh burrs. You're mixing the grounds to ensure that the grounds themselves aren't biasing one side or the other on the portafilter. You can change the size of the jet to slow down the rate, and that may mitigate some of the issues you might be having with an uneven extraction in the group. And so yeah, that's why you kind of change it. So let's go to the next slide and kind of wrap things up. So I think that hopefully we're on time. So why would you change the size of the jets in a group? On the manufacturing side, you would change the size of the jet in the group based upon the flow rate that you're generating from the pump. If you're using a vibration pump, you can sometimes get away with a slightly larger jet because you're already ramping up pressure very slowly. In the case of a higher flow system with a higher pressure system, you may want to slow that down a little bit. So you don't want to reduce the size of the jet in the group so that the distribution of water over the puck is a little more even, gives it a chance to kind of catch up. With the advent of variable speed pumps, though, are jets necessarily variable speed pumps? I think that they still are, but I'm not really convinced why. I think that there's still something to be said, because most variable speed pumps that I've seen, they don't go from like 0 to 1200 or whatever the rating is for the pump. They're typically they're typically functioning within a range of 500 RPM, 1000 RPM, or something like that. They'll never go down to quite 0. So in that case, jets are still kind of important. And then the third question: are there jets in lever groups? No. Jets were not necessary in the early days of espresso because the water floods the chamber at a relatively low pressure and before it even hits the grounds. But there is kind of a jet happening inside even the old lever group machines, because the ports that actually fill water above the screen, above the shower before it hits the coffee, there are typically 4 very small holes, so that because the water envelops a jacket, and that jacket then goes through the small holes above the puck. So it's kind of a different approach to having a dispersion plate. But essentially, it doesn't really have a jet per se. Some of the other lever groups, like the San Marco lever group that actually opens up a gate valve, you can kind of regulate that pre-infusion, especially if you're running heat exchanger and not running super low pressure. In that case, you can kind of have jets to control a lever group machine. But ultimately, when it comes to pressure and flow, the ultimate restriction to determining how your coffee is going to come out is the coffee itself, because every other restriction, every other jet, every other parameter in the machine is either fixed in programming, or it's fixed mechanically by the technician or by the factory when they're setting the machine up. So you can get massive differences of flow rate and pressure just by manipulating the coffee that goes in the portafilter. That's why a single basket has fewer holes, for example, than a double basket, because the extraction rate has to be the restriction has to increase in order to allow the system to build pressure based upon the amount of restriction of the coffee bed itself. So that's pressure and flow on a machine.
Thank you, Mike. Cameras on, please. And we have one question from Mehmet What is the importance of the static and dynamic pressure fluctuations prior to pump?
Unless they're radical, the spring tension of the bypass in the pump will mitigate those differences. So if you've got six bar going to the pump and then it drops down to 3, for example, provided that the pump is sufficiently sized, it's going to bypass anything above 9 bar back into the system anyway. It's only really a problem if you've got V pressure going to the pump that exceeds 9 bar, because the pressure on the inlet side has to be lower than the pressure on the outlet side, and then the bypass will take care of the rest. So it's those kind of pressure fluctuations. You know, you might have a small latency when the spring adapts, but the spring is going to take care of those differences.
So I got texted a question, which it's kind of obvious, but I'd like to get an answer for the group, is why is the hole in the gicleur jet so small?
Anybody? The size of the, okay, when you're dealing with 135 pounds of water pressure, which is what's necessary ultimately to extract the coffee, 135 pounds is a lot of flow. The pumps can push a lot of volume. My father had a classic car in the from the 1960s, and he was concerned that his oil pressure wasn't very good, because when it was running, it was maybe 35, 40 pounds of oil pressure. When it got warm, it looked like it was like 15 pounds. He was panicked, and a technician told him to pull the valve covers off and fire it up and just see how far the water went. So he was only running 40 psi of oil pressure, and when the cam came, with the cam cover off, that 40 psi shot that oil through an orifice that was perhaps a half a millimeter across, maybe a millimeter, about 40 feet. So when you have pressures of 135 psi, it can move an immense amount of water. It'll flood the group. It'll disrupt the puck. If you've ever put a machine back together without the jet, it's near impossible to get the coffee to come out right. You get a little bit of a temperature fluctuation, from one side of the jet to the other, that kind of mitigates some of the extra hot water that comes to the system. But what's happening is it'll flood the group, and you won't get hardly any pre-infusion effect. So the reason it's so small is because that's the restriction necessary to mitigate 135 pounds of water pressure.
So kind of a weird question, but can you explain to some of our non-tech viewers why channeling is bad?
Coffee extraction is time sensitive. So if you've got coffee grounds that will, as the water passes through the puck, it takes typically 20-25 seconds for that extraction to occur. If you have channeling where water gravitates to one side of the puck more than the other, you'll have a portion of that coffee that will have spent the full 20 or 25 seconds being extracted, and the other portion of that coffee, the other portion of that puck where it's not being extracted, is under extracted. So it may only experience, let's say, 15 seconds of exposure to water. So if you've ever pulled a shot, one of the things I used to do when I was doing demonstrations is I would set up a double portafilter filter. I'd line up a series of shot glasses, like 5 shot glasses, and I would just do it a half ounce in each one. I would simply kind of just move them along so that they can see, so that the barista could actually see how the shot was changing as the water was flowing through the system. So the initial extraction where it was pre-infused was relatively dark and relatively sweet, very intense, and then we get lighter and lighter and lighter towards that fifth half ounce where it was very acidic and very thin. So when you have channeling, you'll have some of the coffee which is extracted, on the initial side, but you'll have a lot of that coffee because it's been sitting in the water and under pressure longer than the other, that gravitates toward that more acidic, bitter side. So channeling is, like an imbalance of you're not getting everything that you're supposed to be getting from the coffee. You're getting too much from some of the coffee and not enough from the other.
Thank you. Mike Kahn threw something in. Don't forget that gicleurs are important in multi-group machine because without them, the flow rate is too great when flushing and the pressure at all groups would fall if the group is flushed whilst. Thanks, Mike, for the whilst another is extracting.
That is true. And that's why it's also important to size the pump and the motor to the size of the machine. You know, I have found 104-liter pumps in 4-group machines coming out of factories, which for most, and a lot of the bars in the US, it's kind of okay because, you know, they bought this fancy 4-group machine, but they're really only using 2. But if, you know, a fully operating, you know, a bar that's actually making a lot of, you know, that's running all 4 groups at the same time, you need to have an appropriately sized pump and motor. You do have a problem though if you have a massive pump and a massive motor in a smaller machine like a 2-group machine. You're trying the pump is trying to move a lot of water, but it's not moving a lot of flow, and it can tend to get hot because you're not actually moving, because the water itself kind of cools the pump as it's passing through it. And if it's sitting there just static and running, it can tend to overheat.
So another question I just got texted is, do you see gicleurs in super automatic machines?
Yes.
What's
Anytime
their
that you
role
have
with that piston system?
I'm sorry?
What's their role with that with the piston set system?
Okay. Any time that you've got a distribution of water over a coffee bed, you have to regulate the flow of that water over that bed so that it doesn't channel and it doesn't bias. Even if you can eliminate channeling, the idea is to have an even flow of water through that puck all at the same time. Because even a super automatic espresso machine, you know, they've still got pumps, they're still developing high pressure, even though they're passing in some cases through Teflon lines. The flow is sufficient that you can still have a channeling effect. The jet may not be in the same location, but you have to regulate the flow. Otherwise, everything gets disrupted. The only time that you don't really have to have a jet, I think, is an espresso spin or a spin espresso. Where you're simply using centrifugal force for the extraction.
Matt, Caleb, do you have any questions?
Yeah, I wanted to sort of go back to the that flow chart in the beginning where you talked about the pressures at the different places, you know, in the system with the pump off and sort of with the pump on, and that sort of natural pre-infusion that you talked about in that system. So yeah, the pre-infusion there. So adding the gicleur, the jet valve, you sort of get a natural pre-infusion because when you open the solenoid, there's a minute or a like point in time before the pressure reaches the puck.
That's correct? Yeah.
So then we see a lot of machines that have a pre-infusion built into the programming, which yes, then you can regulate it a little more. But ultimately, in an espresso machine, you know, that's, let's say it's just a semi-auto, no extra electronics, you are getting pre-infusion in that system. But if you add it, you're getting a little more. So what's the purpose? Is it sort of like letting that, for, I guess if you think of a pour over, letting that puck bloom a little bit before the pump pressure take place?
That's exactly what's happening. Because even though the jet has a pre-infusion effect, it's not ideal because the jet has to strike a balance between the flow necessary to extract the coffee and allowing the pressure to build gradually. So if you take the orifice down to, let's say, 0.2 or 0.3 millimeter, you'll increase the pre-infusion effect, but you'll decrease the flow rate to the point where the flow rate through the puck itself is greater than the flow rate from the gicleur, from the jet. So you're striking a balance. That's why when it comes to pre-infusion, you'll have different approaches. So an electronic pre-infusion it'll engage the solenoid valve for, let's say, 5 or 6 seconds, allow the puck to wet. At that point, you've got a relatively saturated circuit. It's kind of giving the system a chance to be fully saturated. And then it re-engages the pump now in a saturated system. So the second time that solenoid comes on, it's no longer really building pressure, it's applying pressure relatively rapidly. Even though if the solenoid opens, it depressurizes, but it's still saturated. Other systems that are like a dynamic or like a mechanical pre-infusion system, there'll be an accumulation chamber. So for example, Simonelli uses an air system, like an air pocket. It compresses air in the system to kind of slow down that flow of water while still maintaining the same jet size, so you can get the proper flow through the coffee, but you're increasing the dwell time. Other manufacturers will actually have an accumulation chamber with a spring on it, and as the water flows into the system, it compresses that spring, and once that spring becomes fully compressed, then it applies the full 135 pounds of water to the group. That's kind of a gradual one, but that pressure will actually increase as the spring compresses. An E61, on the other hand, has a different system. It has a pressure regulator built into the bottom of the group that is very much like the pressure regulator in the pump itself. So what's happening is that spring might be set to, let's say, 20 pounds. So anything that exceeds 20 pounds of water pressure to the group is actually bled by that pressure regulator into a chamber below it. And then once that chamber fully saturates, it has no place else to go. Then the full 135 pounds of pressure, because it can't open anymore, is then fed to the coffee. So whereas like an E61 will have you'll get an initial 5 or 6 psi of water pressure over the puck because of the gicler, but then you'll get a constant flat line of 20 psi during the pre-infusion cycle. And then as soon as that chamber is fully saturated with water and has no place else to go, it will then shoot up to the 135 pounds of group pressure. Whereas the accumulation chambers that are spring-loaded, they'll hit 5 and they'll slowly climb to about 20 and then shoot. So you get a different pre-infusion curve. Whereas the electronic ones, it'll saturate at sometimes a relatively high pressure, but it shuts everything down to give the water a chance to kind of soak in. Yeah. So it's a little bit different. The electronic versions don't work on multiple group machines very well because you have to kind of stop the other groups from brewing while you're pre-infusing the other one. Mike Myers was showing me a 4-group, I think it was a San Marco he was bringing in that had electronic pre-infusion. It was one of the first machines that had electronic pre-infusion. And he said, it's awesome. He'd line up 4 groups and he'd push one button, then he'd push the other and push the other and push the other. And he thought it was cool. It would pre-infuse on one group and then start to brew. When that was done, it would pre-infuse the second group. And then when that one was done, and it would move on, one by one. And I said, that's awesome. You've got a 4-group machine that works like a 1-group. And that in part is like the early GS Marzocco's, for example. You've got a 3-group machine, you've got a paddle group, you've got pre-infusion because you can infuse before you engage the pump. It's awesome. But unless you can move all panels simultaneously, you can only pre-infuse 1 group at a time because the pump is running otherwise. And I think that was, other manufacturers with multi-boiler or with individual, they were trying to do the same kind of static or electronic pre-infusion. We're encountering the same thing without naming names. Unless you had separate pumps, electronic pre-infusion can only work 1 group at a time.
One more Gicler question here. We all know that it's kind of the bane of our existence because it's usually on the hot side. One tiny speck of mineral deposits just screws up the whole thing, and we're in there cleaning that out. How important is placement on, in the system, right? It always seems to be on the hot side. I can't think of one on the cold side. I understand the flow meter needs a certain flow rate to be accurate as well, but like could that jet valve be put in the system somewhere earlier on the cold side that would then potentially reduce the amount of mineral deposits that build up there?
No.
Yeah.
Okay. The placement of the jet and the size of the jet is determined by how much space it has to fill. So, for example, a Chimbley has a solenoid valve. This is on the older machines. That's a little bit further back on the group. So when that valve opens up, it's actually filling a little bit more. There's a bit more space that it has to pressurize between that solenoid valve and the puck. So the size of that valve, the size of that gicler is affected by the space that it has to fill. That's why some machines you'll see more of a gradual flow of water, or you'll press the button and you hear that kind of whoosh, and then it begins to flow. That has to do with the distance between the solenoid and the puck itself, and you size the meter to regulate how quickly that area fills up. If you have hardly any area at all, then that jet needs to be a little bit smaller. But no, it's if you're on the cold water side, you're going to be before a heat exchanger or before the individual boiler, for example. And you've got too many other factors happening, because whenever you take water and heat it up from cold, you have about a 4% expansion. So if you've got a closed system running 92 degrees Celsius, for example, for an individual boiler, that water is actually expansive. So as soon as you hit that solenoid valve, you'll have this kind of surge, this explosion of that expanded water over the coffee puck, and the jet is designed to mitigate that. I'm running into that with a system that I'm designing, where we're trying to have an atmospheric delivery of hot water in a closed system, which is very difficult to do, because even though you're not generating steam, like in a brew boiler, for example, you are expanding that water, and that expansive water is kind of an explosive force. That's why you see, like on some machines that have dedicated boilers, and you look at the pressure gauge, you set everything to 9 bar, everything is great. You've got 3 bar of water machine, but for some reason you're reading like 14 bar on the gauge, and the reason for that is because you've got check valves in the system. So as that water expands in that boiler, because now it's hotter, that 3 or 4% expansion that normally would go to an expansion valve, you only have to drop like 1 drop of water to mitigate that pressure. But if that expansion valve is stuck or blocked, that expansion will generate 13 or 14 bar, and it's actually expanding into the gauge instead of the expansion valve. But as soon as you open up that solenoid valve to relieve that pressure, if the jet is on the input side of that boiler, you'll have 4 or 5 essentially excess bar of pressure that's going to push through and disrupt the puck. And that's why the jet has to be where it is.
We have time for one more question, you guys, because we all have a hard stop at 9. Matt.
So this is borderline like barista question almost, but I loved how you were talking about coffee being kind of the end filter pressure, kind of how that creates a balance between this pressure and extraction. And I think there's a lot of great information that sits in there that's really valuable for the barista, but also for the technician. So when you're looking at a pre-infusion that's handled by needle valves, it kind of echoes kind of Caleb's question about the purpose of the gicler and then other pre-infusion methods. That really does change the process of the barista, and even just the understanding of how this entire mechanics system works from a technical perspective. And I've had a really hard time kind of trying to explain the differences between like how that much a pre-infusion really impacts overall extraction. But how important do you think that is for the technician to really understand those massive changes in pre-infusion to wet that bed fully saturated versus maybe some other systems that don't utilize that?
Well, all systems are designed, every espresso machine is designed with some kind of pre-infusion effect, either with jets or electronics or something. That's why from a technician standpoint, if you've got a plugged gicleur, that means that you have to fix it. You can't simply leave it out, as a lot of technicians have done, because it really affects the whole balance of the system. So, for example, there are some machines now where you can actually use a needle valve to regulate the flow of water through the group. And while it's kind of an interesting toy, if you're manipulating the flow of water through the group itself, you're not letting the coffee be the restriction. So ultimately, it always comes down to this. There cannot be any argument as far as I'm concerned. The ultimate jet, the ultimate determination of flow is the coffee. Everything else is designed to create a level playing field. The pump pressure, the orifice of the jet, the system design, everything up to the shower itself is a fixed level playing field designed to produce a consistent, predictable, same time, every time kind of thing. The coffee itself is the only variable, and that comes down to the grinder. That's why grinders are now important. It used to be grinders were like give me the cheapest grinder you could find, because no one wants to pay the extra money. Exactly. If I just 30 seconds. I was judging barista competitions 20 years ago in Boston, and I was talking to one of the judges for the final round, and there was a competitor from Australia that came in, and everybody was using the industry standard Mazzer Super Jollies at the time, and they took the Super Jolly and set it aside, and they brought in a Mazzer Rover, and they used the Mazzer Rover instead of the Super Jolly for their grinder, which you can't do now. You can't change grinders anymore, and they can't change grinders because they won the competition because they aced all of their espresso shots. All their espresso was off the charts, and that was usually competitions are won by like 1 point or 2. And I was talking to the judge who was a export manager for Brasilia at the time, and he said, "Oh yeah, they swapped the grinders. That's why they won, because it all came down to the grinder. The grinder determines that the flow, the restriction, the consistency of the filter bed. That is the ultimate determination of how everything works. Everything on the shower side all the way back, that's a flat line. That's a predictable outcome. That's how you set up the machine as a tech. That's how the engineer sets up the machine when they're designing it. That's the level playing field. Everything comes down to the barista, how they're distributing the coffee in the puck, how they're grinding the coffee, the roaster, how they're roasting the coffee. Everything comes down to the coffee. That's the only variable. So if your coffee sucks and the machine is okay, if your coffee sucks, it's all on the barista, because he's got to know his craft.
What a great way to end this.
Mm-hmm. Yeah,
I want to say thanks. I've got to run.
We're gonna wrap it up. Caleb, have a good weekend. Thank you. Matt,
yep.
Thanks for your participation. Mike, anything else to add before we close this session out?
No, I talked too much already, I think.
Okay. Next week's episode
Awesome show, guys.
Next week's episode is Dispatch 101, where Caleb, myself, Mark Roby, Kurt Benedict, and a surprise guest who works as a facilities person will be fighting about the best ways to dispatch. For those of you that joined us, have a great weekend, and hopefully we'll see you next week. Gentlemen, thank you for your time.
Great. Thanks.